A data center can keep its servers powered after the grid fails and still be moving toward shutdown. The processors continue working, so they continue producing heat. A complete emergency plan has to carry electricity into the racks and carry that heat out of the building. Inside a server rack, nearly every watt of electrical power eventually becomes heat. Processors, memory, storage, and power supplies release it into a confined stream of air. Fans pull cooler air through the front of the equipment and discharge warmer air behind it. Those fans only move the heat into the room. An air handler, or another room cooling unit, has to draw the warm air across a coil. Chilled water, or refrigerant, then carries the energy farther through the building. Pumps maintain circulation, valves direct the flow, and chillers or other heat rejection equipment finally move the energy outside. The result is a chain rather than a single air conditioner. A powered server fan cannot compensate for a stopped water pump. A running pump does not help if a valve remains closed. A chiller with electricity cannot cool the room if its controls have not completed the restart sequence. Cooling depends on useful flow through every required link. The electrical handoff begins with the uninterruptible power supply, usually called the UPS. Its batteries, or stored energy system, bridge the immediate interruption. This keeps selected equipment operating while standby generators start, stabilize, and accept load. The cooling system may follow a different timeline. Some facilities place room fans, control systems, and chilled water pumps on protected power. Large chillers may wait for generator capacity, then follow a manufacturer and site-specific restart procedure. Sensors, control networks, valves, and motor drives also need to return in the correct state. For this reason, generator availability is only one part of the evidence. Engineers also need to know which cooling loads are connected to emergency power, how they are sequenced, and whether the electrical capacity is sufficient when several motors start. A generator can be operating normally while the thermal system is still completing its handoff. The rack now has two operating margins. The electrical reserve describes how long protected power can carry the computing load. The thermal margin describes how long the room and cooling loop can absorb continuing heat without leaving acceptable inlet conditions. These margins come from different equipment and should not be treated as one countdown. Battery capacity, server load, and generator behavior shape the electrical side. Room volume, rack density, air mixing, water volume, equipment mass, and the state of the cooling plant shape the thermal side. Temperature also varies across the room. A sensor near a cool return path may show a stable value, while the inlet of a dense rack is warming. Operators therefore pay attention to location and rate of change, not only a building-wide average. One approach is to protect more of the cooling chain. Fans, pumps, controls, and selected plant can remain on UPS or emergency power. The design still has to account for motor starting, staged loading, and the order in which equipment becomes useful. Another approach stores cooling before an interruption. Intel documented a facility that used a chilled water reserve for emergency cooling. During ordinary operation, the plant prepared a cold inventory. During a transition, pumps could circulate that stored water through the cooling coils while the normal chiller path recovered. The tank shifted when the cooling work occurred. Its useful duration depended on the stored volume and the actual heat load. The building supplies a third, smaller buffer. Air, water, metal, concrete, and equipment absorb energy as their temperatures rise. This thermal mass slows the change, but it does not remove heat from the site. Its value depends on the physical room and becomes smaller when power density is high or airflow is poorly distributed. These measures are often combined. Protected circulation keeps the transfer path active, stored cooling bridges a known interval, and thermal mass softens the remaining transient. The design objective is enough verified margin for the cooling plant to recover or for operators to reduce the computing load in an orderly way. A useful emergency plan maps dependencies rather than listing individual machines. Which server rows remain powered? Which air movers serve those rows? Are the pumps and control valves on the same emergency path? When can the chiller accept load? Which control network issues the commands? And what happens if one sensor or drive does not return? The answers form branches rather than one universal sequence. A site with redundant chillers can still depend on a common pump or control panel. A generator may have enough steady capacity, but insufficient allowance for simultaneous motor starts. A powered control cabinet may still lack a valid sensor signal. Resilience depends on the complete path required to move heat. Thermal modeling helps engineers estimate what can happen after cooling is interrupted. A model can represent heat load, room volume, airflow, equipment mass, fan status, and cooling response. It can also identify local hot spots that disappear inside an average temperature. The model is only as useful as its assumptions. Commissioning connects those assumptions to the real building. Engineers can interrupt selected feeds under controlled conditions, verify automatic commands, measure temperature response, and compare the result with the design case. Repeated drills can add alternate failures. A pump that does not start, a valve that stays closed, a sensor that reads incorrectly, or a generator that returns without all cooling loads connected. These exercises reveal whether breakers, controls, mechanical equipment, alarms, and human procedures change state together. During an actual handoff, operators need several kinds of evidence. Rack inlet temperatures show what the servers are receiving. Water flow and pressure readings show whether heat is leaving the room. Fan and pump status confirm motion, while generator load and UPS runtime show the remaining electrical margin. The direction of change matters. A temperature within its normal range, but rising steadily may call for action earlier than a stable reading near the upper limit. Operators compare those trends with the expected restart sequence and the measured behavior from previous tests. If cooling returns within the verified margin, the computing load can continue. If conditions continue moving in the wrong direction, operators can migrate workloads, reduce processor demand, or shut down selected equipment in a planned order. Load reduction lowers both electrical demand and heat production, preserving more control over the remaining transition. Normal utility power does not end the process immediately. Equipment has to return without creating a second unstable handoff. Batteries and thermal reserves need to recharge. Cooling plant must settle into its ordinary configuration, and recorded alarms and measurements should be reviewed. The useful outcome is a comparison between the intended sequence and the one that actually occurred. Unexpected delays, incorrect sensor readings, or missing loads can lead to changes in controls, maintenance, procedures, and capacity planning. A data center survives a power interruption when power continuity and heat removal are treated as one timed operating system. Batteries and generators keep selected equipment energized. Air, water, and mechanical plant carry away the heat. Sensors show the remaining margin, and operators have a tested point for reducing load. Backup power is necessary, while continued operation depends on the coordinated system around it.